Hello, today we're going to talk about interpretations of the derivative, and we're going to be introduced to Leibniz notation. So we'll jump right into this here. Our objectives are I can use Leibniz notation, and I can interpret the meaning of a derivative within a problem and state appropriate units. So a couple different notations for the derivative. This one we've already seen a little bit here, this f prime of x or y prime. Standing for the derivative of y or the derivative of f of x. Leibniz notation is a little bit different here. Leibniz notation is actually in this form of a fraction is dy dx. So this means the same thing as saying f prime of x. Actually, I shouldn't use f prime, excuse me. I should say y prime because our function here is y. And we put calculator notation here because this is the same notation that you'll see on your calculator. We will be able to take derivatives from graphs on our calculator, and the notation that they use is dy dx. So just to show you quick where Leibniz notation comes from, it does come from the average rate of change, or from our formulas for rate of change. This formula here is our formula for slope. Y2 minus y1 over x2 minus x1, which is the same thing as the change in y over the change in x, and that symbol there is delta, so delta y over delta x. Derivatives are the instantaneous rate of change, and so in this case we're looking at the limit now as x2 and x1 are getting infinitely close to each other, so no longer are we looking at this as a secant line, but we're looking at this as a tangent line, or the slope of the tangent line. So remember, that's why, or slope of a tangent line is another way to say the instantaneous rate of change or derivative. So this notation directly comes from that. That dy dx then is used because it's finding the slope of that tangent line there, or the value of the limit as the x coordinates get closer and closer together. There's some nice things about Leibniz notation. The first one is that it really reminds us what the units are for the derivative. So it really reinforces that to us. Units for y are going to be over our units for x when we're doing these problems. That dy dx notation, I think, makes that an easy concept to remember for us. Our units for y have to be on the top because dy is there on the top, and our independent variable x is in the denominator. We can also think, if we can kind of separate our notation there for Leibniz notation, we can also think of it a little bit differently. And so what Leibniz notation can represent here, or how we can write it, is it's the derivative. So this part right here stands for the derivative with respect to x. And so right now that doesn't mean a ton to you, the derivative with respect to x. We're going to move into examples where we're not taking the derivative with respect to x anymore. Our independent variable will be something different, and we're taking the derivative with respect to a different variable. But in this case, that d over dx is telling us that we're taking the derivative with respect to x of our function y. And so what we can do with this is we can actually look at this with different functions as well, using Leibniz notation. So we could say the derivative with respect to, so here's what I have written there. But we can do this with really any function. So we can say the derivative with respect to x of a. We could say the derivative with respect to x of, anything, frankly. So this notation works just as well as saying y prime or a prime or f prime of x. The notation is just as useful in those cases. So here we have is a graph that represents the position of our function in meters, and our time t is in seconds. So we do have the units here on our graph. We have this red curve. We've got what looks like a piecewise function here. If you aren't familiar with Latin, which I'm assuming most of us are not, the S stands for the Latin word spatium. I hope I'm saying that right, which means distance and space, or distance or space. So that's where that comes from when we use S of t. That's generally used for position, and that comes from the Latin. What I'd like you to do is to just pause the video, find S of 6, S of 1, S prime of 6, and S prime of 1, and state their meaning using units. All right. So the first one we have, let me change colors here. I don't want to use red for this whole thing. I'll use blue. So S of 6 here, if we go to our curve on the x-axis, when t, or time, is 6, we get 20. Whoa. There we go. we get 20. And our units here is 20 meters. So state the meaning using units. So after 6 seconds, our whatever our object is, the object is 20 meters from, or 20 meters away, we can say. There we go. S prime of 6 is asking us for the derivative at 6, or the instantaneous rate of change. We can also think of that as being the slope at 6. And the slope is 0 here. And our meaning of this now, since it's a rate of change, we have to describe this as a rate. So it's no longer just meters or just seconds, it's meters per second. So at 6 seconds, the object, whatever it is moving at a rate of 0 meters per second, which in this case means it's not moving, but we want to make sure it's still described as a rate, and we have those units in there to make sure that we've articulated that we know the derivative is a rate and the units are meters per second. So just like we talked about with Leibniz, our dy over dx. So S of 1, this is going to be pretty similar. I'm just going to change colors one more time. S of 1 here looks like it's going to be about 12, but I'm not sure if that's 12. Let me do S prime of 1 first here and make sure that's exactly 12, because it looks like it's going to be a little more than 12. So your slope at 1 is the slope of this line here, and it looks like we go up 10 units and over 4. So our slope would be 10 over 4, which simplifies to 5 halves. And so in this case, we would say that at 1 second, the object is moving at a rate of 5 halves, or 2.5 meters per second. So in this case, if every 2 seconds we're going 5 units, or we're moving 5 meters, that means after 1 second we're moving about 2.5 meters. So S of 1 would be 12.5 meters. And so our meaning here is after 1 second, the object, let's say, is 12.5 meters away. So again, with calculus here, we're not just focusing on the mechanics of actually solving the problems. We have to have that conceptual understanding as well. AP tests and AP questions are going to ask you to explain their meaning using units, and explain the meanings of derivatives and different functions that we have. So make sure it's not just, you're not just saying, well, I'm comfortable evaluating and that's enough. The meaning part, that is just as important as the mechanics of solving these problems. So let's do one here using some of our notation for derivatives, where we don't have a graph, we're just interpreting some values for each of these questions. So what we have here, and you can pause the video to write this down, but what we have is the cost C in dollars of building a new house with A square feet of area is given by the function C equals f of A. So for a reminder for myself, A is our independent variable in this case, so our units here are going to be square feet. Think of it along the x-axis. And then our units for our dependent variable, which is the cost, would be dollars. So as we're going through and answering these questions, I want to make sure I have those in mind while I'm answering these. And I want to move this up just a little bit so I have a little more space to write these out, because my formatting is a little different on my iPad than it is on my computer screen. All right, so let's get into the first one here. So it says f of 1,000 equals 120,000. So what this says, 100,000 is representative of the area of the house. So a 1,000 square foot home costs $120,000. Okay, let me change colors here just to keep these a little more clear. This next one really is taking the slope, or the average rate of change. I'm going to write AROC up here, the average rate of change, between 0 and 1,000. So f of 1,000 minus f of 0 over 1,000, really 1,000 minus 0, and that equals 120. So what this is telling us is the average, oops, see if I can do that again. The average cost per square foot from 0 square feet, I'm going to write it square feet like that better, to 1,000 square feet is 120, and now this is the average rate of change, so it has to be as a rate, dollars per square foot. So the average cost per square foot from 0 to 1,000 square feet for a home is $120 per square foot. So again, our units are representative of that rate here. So we are showing that this is a rate. All right, finally here we have f prime of 1,000 equals 50. So this is the instantaneous rate of change. This is IROC. Again, it's a rate of change, so we have to make sure we're articulating our units as a rate. And because it's the instantaneous, we can say specifically at 1,000 square feet. So a 1,000 square foot home, the rate of change for the rate of change for this function is increasing at a rate of 50. And again, our units need to be representative of a rate. So $50 per square foot. Oops, it should be down there. Okay. So again, the interpretations here when we're going through these are just as important. And your wording might not have been the exact same as mine. That's fine. You just have to make sure for this last one, you're articulating that this is increasing at a rate of $50 per square foot, and it's happening specifically when we have a 1,000 square foot home. It's that instantaneous rate of change. All right, we'll do one with Leibniz notation here. This one's similar. You can pause the video to write this down for yourself. But we have a cost again. This time we're extracting T tons of ore from a copper mine. So this is tons of ore along our x-axis, and the dollars again cost along our y-axis. I'm going to slide this stuff up again because there's a little more space for my iPad here. We have Leibniz notation, so it's saying dc dt. So this again is the instantaneous rate of change. So this is the same thing as saying, we can think of this as c prime, and we're going to actually write that after we fill out the meaning here. But this tells us our t, our independent variable is 2,000, and our dependent variable here, c, well, actually this is the rate, excuse me, is 100 here. So since it's the instantaneous rate of change, I want to be able to articulate this. So when 2,000 tons of ore have been extracted, so specifically at that time, instantaneous time, what we know then is the rate of change of the cost is increasing, so it's positive, oops, increasing, there we go, at a rate, the rate of change is increasing at a rate of $100 per ton. Now again, your wording, if you wrote this before me, it doesn't have to be the exact same. We want to make sure we're specifically saying that it's at 2,000 tons of ore, or when that's happened, the rate of change is $1,000 per ton. And writing this in f prime notation, well, our dependent variable is c, so c prime of 2,000 equals 100. All right, last one here. I'd like you to try this one on your own. I've got an extra little graph that I don't need, or extra axis I don't need. You've got 4 parts here, so if you want to pause the video for yourself and write down what each of these represent in this example. All right, I'm going to set up my table here. T is the years after 100 or after 1980, so this is T is in terms of years. Oops, I don't want to put T there. Let's do years. So we can do years. And then this is the population in millions. All right, so f of 6 equals 83. 6 represents the years after 1980, so our meaning here is in 1986. The population of Mexico was 83 million people. For the next one, f prime of 6, this is the instantaneous rate of change. It's the derivative. So we need to make sure we're writing this as a rate. F prime of 6 equals 2. Well, we're looking at this again in 1986. And now the 2 has to be our rate. So in 1986, the population was increasing at a rate of, and the 2, if we remember Leibniz notation with our units, is units for y over the units for x. So increasing at a rate of 2 million people per year. So again, we've said in 1986 specifically, so we're looking at that instantaneous point, and then we're telling the rate, which is a rate of 2 million people per year. In this case, we're increasing. All right, f inverse of 95.5 equals 16. Inverse means we're flipping our x and y coordinates around. So this is actually our dependent variable. This is our population, and t is actually going to be 16 here. So the population, we'll start there, of Mexico was 95.5 million people in, and it's 16 years after 1980, so that's 1996. All right, the last one here, I hope you got this one. This is kind of a goofy one. We're looking at the derivative of the inverse now. So again, it's a rate, an instantaneous rate of change. But now we're not going to do our units for y over our units for x. Because it's the inverse, we're actually going to put our units for x over the units for y. So let's try this here. So when the population was 95.5 million in Mexico, the population, again, it's positive 0.46, so the population was increasing at a rate, and now again, I've expressed it as a rate, and our units are going to be flipped. So our units are our x is on the top, so 0.46 years per million people. It's kind of a weird way to think of this. It's 0.46 years before we have another million people, but because it's the inverse here, we flip those units around, and so the rate represents, like I said, years per millions of people. So I hope that helps. Good luck with your homework.